Alright guys, here you go. Last video, last 3 questions, starting with question number 8. Illumination. The intensity I of illumination from a light source is inversely proportional to the square of the distance, d, from that source. So we have everything to write our equation. I is inversely proportional, meaning it's k over something, where k is our constant of variation. And the thing that it's inversely proportional to is the square of the distance d. So that means it's d, but squared. So d squared. There's our equation. Now we're going to find out enough information to solve for k. Just watch. Watch what they tell us. They're going to tell us, okay, intensity is 320 candela at a distance of 10 feet from the light source. So that right there tells us the I and the D, right? I is 320. K over D is 10. And that's 10 squared. Of course, 10 squared is just 100. And now to solve for K, I have to multiply by 100 on both sides. That would give me K is equal to 320 with 2 extra zeros, or 32,000. So there's your K. Now once you have that K, we do the same thing we always do. Plug it back into my equation. So it's 32,000 over D squared. Okay. And then now just plug in the new numbers that they give us for the next part of the question. Next part says, what is the intensity at 5 feet from the source? What is the intensity at 5 feet? So in other words, the D is changing from 10 to 5 now. What happens? It's 32,000 over 5 squared, which of course is just 25. So easy, just plug those numbers in, right? Plug those numbers in. I'm going to just cheat and use a calculator here. So I've got 32,000 divided by 25, and that's 1,280. So I is 1,280. And what is the unit of measurement here? This is light intensity, and it's measured here in candela. So candela is the light intensity at 5 feet. Notice that this is a larger light intensity for a shorter distance. And that makes sense because it's inversely proportional, right? Inversely proportional means as one variable gets farther away from 0, the opposing variable gets closer to 0, and vice versa. So intensity was only 320 when it was 10 feet, but at 5 feet, now it's 1,280. Okay, next question is a follow-up question, which is, how far from the light source will intensity be 400 candela? Okay, so we're going to take our same equation from before. This I is equal to 32000 divided by D squared. Right here, yeah. And now we're going to input the new information. New information is that the intensity should be 400 candela. So that's the I part, right? I should be 400. So notice what we mentioned in the previous theory part. It's always the same. They give us all the numbers except for one, right? So that we can solve the equation for that missing thing. In this case, the missing thing is the D, the distance. Now 420 candela, that's slightly larger than 320. So slightly higher intensity means I should be a little closer. So the distance I'm expecting to be a little less than 10. But let's see what happens. Okay, how do you solve something like this? You multiply both sides by D squared, right? So you get 400 D squared is 32,000. Then you divide 32,000 by 400. And that gives you 80. So D squared is equal to 80. Now, I'm only concerned really about with the approximation. So I'm just going to go ahead and take square roots. D is the square root of 80, which is approximately 8.94. 8.94. And what is the unit of measurement here this time? That one is in feet, yeah? Because the distance was being measured in feet. Okay, that all makes sense, right? The distance is about 8.94 feet. So a little closer for slightly larger light intensity, 8.94 feet. Okay, great. That's number 8. On to number 9. Safe load. The safe load that a rectangular beam can support varies jointly. Let's start highlighting things. So the safe load varies jointly as the width and the square of the depth. Okay, so far I'm not finished, but save. Let's give these things these variables some names here. Let's call safe load S for safe, and width we'll call W, depth we'll call D, but it's the square of that, so it should be D squared. So far, the equation looks something like this. Safe load is varying, so some constant of variation, jointly with the width and the square of the depth. Okay, but we're not finished reading the sentence. It says inversely as its length. Okay, so that means let's call the length L for length, right? Varying inversely means I should have the L on the bottom of the fraction. So there's my full equation. Now I'm expecting them to give me information that will enable me to solve for that missing K, the constant. Let's see what they tell me. So the beam is 4 inches wide. Okay, so that means W is 4. Sorry. It's 6 inches deep. So that's the D is 6. 25 feet long. So the L here is 25. And can support a safe load of 576 pounds. So that means the S is 576. So notice everything except for K is now accounted for. So I can fill all those numbers in. K times, oh, I'm sorry, I wrote W here. What was I thinking? That should have been a 4, yeah? I think I may even have said 4, but wrote W. Okay, so that's K times 4 times 6 squared over 25. And now that I have that, I'm just gonna erase this stuff because it's starting to look messy. So let me just clean things up a bit. Okay, so now let's solve for this thing. So 4 times 6 squared is 144. So I've got 144K over 25 is equal to 576. Okay, how do you solve for something like this? You just multiply by the reciprocal, right? By 25 over 144 on both sides. Here on the right, cancel, 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 you have K. And on the left, we got 576 times 25 divided by 144. And that turns out to be exactly 100. Oh, nice, nice. Okay, so come back now. We know K. We're going to input K for K. And then W, D squared over L, right? Great. Now, what are we told next? Okay. Now it says find the safe load. So we're going to find S, right? For the beam, same material, 6 inches wide, 10 inches deep, 20 feet long. So S is equal to 100, 6 inches wide, 10 inches deep, square, don't forget to square that, 20 feet long. I just punched all those numbers in. 10 squared is 100, divide by 20, let's get 3,000. So S is equal to 3,000. This is a safe load. The measurement here is pounds. So with those dimensions, it can hold 3,000 pounds. Same material. Okay, cool. All right. Yeah, this is really interesting to me if I think about it, actually. Very useful for like civil engineering. And then you have this observation that the beam can hold so many pounds based on those variables of dimension, and then that enables you to calculate how much a scaled up version of that same beam, or maybe even varying, doesn't have to necessarily be the scale up. You could alter the components of the beam dimensions at different rates, right? Okay, anyways, number 10. Metabolic rate. Metabolism is the sum total of all physical and chemical changes that take place within an organism. Okay, good to know. Or according to the laws of thermodynamics, all of these changes will ultimately release heat, so the metabolic rate is a measure of heat production by an animal. Okay, also good to know. Now, not super necessary for us in terms of actually solving the question mathematically, but it's good to know. Biologists have found that the normal resting metabolic rate of a mammal is directly proportional to the 3/4 power of its body weight. Okay, so this sentence is where we get our equation from. What are we looking at here? The metabolic rate of an animal, that's one variable. That's what we're trying to figure out, I guess. Is directly proportional to the 3/4 power of its body weight. Okay, So let's call m the metabolic rate. And we'll say W for weight. So this says the metabolic rate is directly proportional, so some constant of variation, to the 3/4 power of its body weight. So that means W to the 3/4 power. Now, if you like, you can think of this as W to the 3rd power, and then you take the 4th root of it. That's what that means. But you can actually just input fractional powers into a calculator. So that's what I'm going to do when I punch things in. You can use the Desmos calculator, or just actually scientific calculator. You have to use a scientific calculator. I forgot. Okay, so see, now they're gonna give us information enabling us to solve for K. Let's see what they give us. They say, for reference, resting metabolic rate of a person weighing 75 kilos. 75 kilos is 75 watts. Okay, that's nice that these are both happen to be the same. 75 kilos, 75 watts. So which one is which? Not that it matters because they're both the same, but let's say I didn't say they were different. Which one is which? Kilograms is the measure of weight, right? So that's the W. So K times 75 to the 3/4 power should be equal to the watts of 75 watts. Okay, now let's solve for K. K is 75 divided by 75 to the 3/4 power. I'm just going to punch that in. And I got K is about 2.9428, approximately. That's an approximation, so I'll do the squiggly equal. Okay, now that I have K, I'm going to come back to my equation, plug that thing in, 2.9428. I'm going to keep some extra decimals because ultimately I'm going to just round my answers to the nearest single decimal place. But I gotta make sure I have sufficient extra digits. In fact, it's best to just keep the entire thing just saved inside your calculator if you can. Okay, this is times W to the 3/4 power. Yeah. What question are they gonna ask? Let's find out. What's the question now? Estimate the resting metabolic rate of a brown bear weighing 450 kilograms. Okay, so they're giving us a new weight. We gotta figure out the new metabolic rate. Yeah. Let's plug that in. So we're solving for m, meaning m stays a variable, 2.9428, and W is 450 to the 3/4 power. Okay, that's easy because why is that easy? It's easy because everything's already just numbers on one side, right? So I'll take my answer. I'm gonna actually have it saved in my calculator. So I'm going to use that answer and then multiply by 450 raised to the 3/4 power. Okay, and I'm going to get m is approximately 287.5. And what is the unit measurement here? This is watts. Watts. So this is the metabolic rate for a brown bear weighing 450 kilograms. 450 kilograms. Wow, it's very heavy. It's like almost a ton. Or is that a ton already? Okay. Oh no, actually, yeah. So I got 10. Okay, let's look at the next question now. So we just answered so far up until this position, right? We got a new question now. What is the effect on the metabolic rate if the body weight is multiplied by 4? What is the effect on metabolic rate? Okay, so that's a general question. Not talking about the bear anymore, talking about any mammal, right? And this is an interesting question here to me. How does multiplying the body weight by 4 affect things? So here's how we're gonna do that. We're gonna take the original equation that we had here with the K, right? Actually, no, I'm gonna erase to make some space. Erase this word here. Oh no, not that word. This part. Okay, so I got my equation, right? And the only thing I'm going to change with that equation is I'm going to compare that to what would happen if instead of my original weight, I have 4W instead. 4 times the weight. What would happen? Okay, my K would be the same, right? And I'd have 4W now. That's going to be raised to the 3/4 power. But what happens? That's 2.9428. What happens if I raise this to the 3/4 power? That's the same as 4 to the 3/4 power times W to the 3/4 power. Now let's compare. Compare my original, which was over here. Okay, that part stayed the same, right? So you can effectively ignore that. This W to the 3/4 stayed the same, so you can ignore that. So this guy's gone, basically. That's gone. What changed? Well, the only thing that's new is this 4 to the 3/4 power now. So what's the change? The metabolic rate was multiplied now by 4 to the 3/4 power compared to what it originally was. And what is 4 to the 3/4 power? Punch that into the calculator. It's about 2.8. Okay, so let's write this one. You know, this question to me merits ascendance. What happens? What's the effect if body weight is multiplied by 4? Then metabolic rate increases, or let me say it not increases, let's say is multiplied by 4 to the 3/4 power, which is approximately 2.828. Okay, cool. So now one last remaining question. What is the, here, let's write that. What is the approximate weight? So this time they're asking for the weight, and they're going to give us the metabolic rate, yeah? Of a animal with metabolic rate of 250 watts. Okay. So for that, guys, I'm going to erase all this old work, come back to that equation that I had, and answer that portion of the question. And, you know, I'm only doing this because my space is somewhat limited. For you, if you're working this out, just continue working on the same paper right below it, yeah? Or take a new paper, just keep writing. You don't have to erase like I'm erasing. Not that anybody has been doing that, really, so, okay. Okay, so let's solve this thing. This time they're giving us 250 as the M, right? That's the watts. So fill that in for M. And we're gonna solve for W this time. So first step is to divide by that 2.9428, right? So 250 divided by 2.9428 is equal to W to the 3/4. How do you undo 3/4? Well, you raise it to the 4/3 power. So this whole thing raised to the 4/3 power. And that's what W is going to be. So I'm going to take this whole big ugly thing. Let me make it a little easier for you to follow here. So if I were you, I would just plug in the whole original value. And in fact, I'm going to go further digits, write as many digits as I can for this bottom number, because I have it stored in my calculator. Okay, and then this, I'll just tell you what the approximation is at so you can see what's happening. So that approximation is about 84.95212. I'm raising that to the 4/3 power. Okay, when you do that, you get W is approximately 373.45. And what is the unit of measurement here? That's weight. This is in kilograms. Let's just think about if this makes sense here for a second. 75 kilogram person makes 75 watts. A larger animal should make more. This case, we're looking at a 250 kilogram animal, and indeed it does make more at, or it weighs more, I mean, at 373 pounds. I'm sorry, kilograms, not pounds. What about the brown bear? Brown bear was even heavier at 450 kilograms, and that made, what did it make? Oh, I think I erased it already, but it was higher than 250, which it should have been because it was a heavier animal. All right, guys, that's it. Thanks for sticking with me. Have a great day. We're finished with chapter 2, and now we're going to move on to reviewing. Okay, see ya.